Okay, when I signed in, it told me that there was technical issues, so I can't actually see the assignments today, it looks like. So what questions do you have on assignments, but you have to tell me the question itself? Okay. Maybe something like okay. So okay. So I'm going to take, remember when we're doing substitution, we're trying to find an inside function and the derivative of the inside function somewhere in here. And so this looks like the derivative of the cosine function, plus or minus, right? So we're going to take g is equal to the cosine of 5x, and then dg is equal to, well, the derivative of the cosine, it's downward slope, so it's the negative sine of 5x times 5 dx because of the chain rule. And so I'm going to find in here, I've got the sine of 5x dx, so if I'll have dg over negative 5 equals the sine of 5x dx. So I get to substitute that in. And so this will be the integral of g to the 5th times dg over negative 5. So that will be the antiderivative there, g to the 6th divided by negative 30 plus a constant. Does that make sense? So this will be cosine to the 6th of 5x over 30. What was the one with the book head? Did we do that one too? Okay. And so if we recognize that the secant squared is the derivative of the tangent, that tells us that we should probably use g as the tangent. So we get that. Other questions y'all have? Yeah. Over what to the x? X to the, okay. Something like that. Something like this. Okay. Let's see, what would I do here? One thing I'd probably try first is pull everything that I can outside the square root. So I can pull out 1x to the 4th outside. let's just try some things, because I don't see right away what I should do, but we'll try. I'll use u. X squared minus 6, so du equals 2x dx. So you get integral of u plus 6 to the minus second there, but you get an extra x in there, so that's probably not good. So let's try something else. That doesn't seem to go anywhere. Let's try just u equals x squared. So we do that. And we get dx equals du over 2x. And so this turns into the integral of 1 over u squared times the square root of u squared minus 6 times du over 2 square roots of u. Sorry, not u squared in there, just u in there. Because x is the square root of u, right? This tells me. Okay, but that doesn't really seem to get us anywhere either, does it? Okay, one last thing that I might try. Let's try u equals the square root of x squared minus 6. So du equals 1/2 x squared minus 6 to the minus 1/2 times 2x dx. We okay with that? Okay, so I've got the integral of, well, I got u up top. I've got u to the 4th down below, or x to the 4th down below. So let's solve for x to the 4th. So that's u squared plus 6 squared equals x to the 4th. And then, let's see here, I've got dx that I want to replace. So dx is equal to du times the square root of x squared minus 6. Those 2's cancel. I've got an extra x, so over an x. Okay, so that's going to be times u again. And then x by itself up here is going to be the square root of u squared plus 6. Okay, so I get integral u squared over u squared plus 6 to the 5/2 du. I sort of want to do a triangle substitution now. Maybe I could have done a triangle substitution earlier. Did it give you any hints on how to do this one? That's weird, but okay. We could probably do a triangle substitution there, but that looks easier with their trick. So you got x squared minus 6 over x to the 8th. So we're going to rewrite this. We're going to factor out a bunch of stuff. So I'm going to leave 2 of those inside. And I'm going to factor out 6 of them outside the square root. And then I'll have an x squared minus 6 over x squared inside. Okay, and the reason they want to do that is because if I take the derivative of 1 over x squared, I get 1 over x cubed at some point with a constant somewhere. So the 1 over x squared goes to 1 over x cubed. And so we want to look at it this way. And then you get the 1 over x cubed. You get the square root of, if I do this division, I get 1 minus 6 over x squared. And then that's where we take our substitution. U equals 1 minus 6 over x squared. So du equals, that goes to 0. This is x to the minus 2nd. So I multiply by minus 2. I get 12. I get x to the minus 3. And I have a dx. So du over 12 equals 1 over x cubed dx. I have the 1 over x cubed dx up there, so I get du over 12 here. So this is the square root of u times 1/12 du. And now I can take the antiderivative of that. So that's u to the 3/2 divided by 3/2 and also divided by 12 and a constant. So that's going to be u to the 3/2 over 18 plus a constant, which is 1 minus 6 over x squared to the 3/2 over 18 plus a constant. That was kind of some strange algebra there at the beginning, but it worked out for us. Reminds me of a problem I did in high school. That, like, I forget exactly what it was, but it was like the cube root of x squared plus 1 over x squared or something like this, maybe. And in high school, my calc class, my instructor, for our final, just gave us a list of like 50 integrals to try and attempt. And this was the only one I couldn't figure out. But then I eventually figured it out like a week later, which was nice. But that was a tough one. I don't remember exactly what it was, but it was something with a cube root and a squared and like a 3/2 root somehow. But it worked out. You just had to find the right algebra to do. Okay. So once you find the right substitution, that's not so bad. Let me try it this way and see if I can do a trig substitution and end up with something similar. Should end up with something similar. Plus. Okay, so triangle substitution. I want this side to be the square root of u squared plus 6. So this side's going to be, let's make this side the square root of 6 and this side u. And I can pick whichever angle I want to be theta. I'm going to make this angle theta so that I'm dealing with the tangent when I have the u over the square root of 6. Tangents derivatives are going to be positive. I'm not going to have to worry about minus signs carried around. I'll use the regular trig functions rather than the inverse trig functions. Okay, so u over the square root that's equal to the sine of theta. So I've got 2 of those, and then I've got 1 extra square root on the bottom, right? Okay, and so I want 2 u's up top, so I'm going to use 2 of the sines, but the other thing that I have is I got the square root of 6 over the square root of u squared plus 6. And that's the cosine of theta. So I've got 1 of those. Does that make sense? So this thing is equal to, but I don't want the square root of 6. I just want the 1 over bit. So I'm going to put a 1 and put the square root of 6 down here. So far, I've got sine squared theta times cosine of theta. I've got 1 over a square root of 6, and then I've still got a du. All good? Okay. To get du, I'm going to use u equals the square root of 6 times the tangent of theta. So du equals the square root of 6 secant squared theta d theta. U over the square root is the tangent, so just bring the square root up and you get u equals 6 square root of 6 times the tangent. There, write that u squared of 6 equals tangent theta. So I get this and then I get this. So I can replace the du with the square root of 6 secant squared theta d theta. So this is square root of 6 square root of 6 sine squared theta cosine theta secant squared theta d theta. And now I can just cancel a bunch of stuff. Well, those are 1. I've got sine squared theta. The secant squared cancels one of the cosines and one of them goes down here. So cosine theta. And then I've got a d theta. So what I have is I've got the integral of sine squared theta over cosine of theta d theta. And what should I do with that? I think I'm going to turn everything into cosines. And then this is equal to the integral of the secant of theta minus the cosine of theta, d theta, which is equal to, we haven't learned the antiderivative of the secant theta yet, but it is the secant is the natural log of the secant of theta plus the tangent of theta minus the antiderivative of the cosine is the minus sign, so this is plus the sign. No, that's not right. The antiderivative of the minus theta cosine. Minus cosines over here goes to positive sign when we integrate, right? Derivative of the sine is the cosine. So the antiderivative of the cosine is the sine, yeah. And then we can just use my triangle to substitute stuff back in. So this is the natural log of, well, the secant of theta is square root of u squared plus 6 over the square root of 6. And the tangent is plus u over the square root of 6. And then minus the sine is u over square root u squared plus 6 plus a constant. And then because this was part of the x one, I have to figure out what x substitution I did up here. What substitution did I do x to get to this guy here? I did, or sorry, u is square root of x squared minus 6. That's divided by the square root of 6, and that's divided by the square root of 6 inside the natural log, so I'm just going to get rid of those because I'm going to absorb them into the constant. Because in the natural log, if you divide by something, you can pull it out with a subtraction, so it's minus the natural log of 6, which is just a constant, so it goes with the constant. Okay, so I've got the natural log of the square root of x squared minus 6 plus 6 plus the square root of x squared minus 6 minus the square root of x squared minus 6 over the square root of x squared minus 6 plus 6 and a constant. Those cancel, I get an x. These cancel. I get that, which looks a lot different than the thing we had before. So maybe part of my substitution was wrong somewhere, but that's the idea behind the triangle substitution. You can kind of turn things into trig functions, which you find a lot more identities and things that you can play with that way. Because they should give you the same thing. I get a 3/2 and an 18. I'm kind of thinking my original substitution was wrong because there was a lot of algebra in here that was maybe done a little quickly. So we'll go with that. Other questions you guys have? Like that? Okay. That one looks a little easier. We're going to take u equals x squared plus 2. So du equals 2x dx. So dx equals du over 2x. And I'm going to replace that inside here. So this becomes, I'm going to leave one of these x's here so that I can cancel it out with this x. Good with that bit? And then this part tells me that u minus 2 equals x squared. This is that. And then I've got the 1/2. Okay. So we had to manipulate both of the substitutions to get parts of the substitution, the actual substitution, both of the equations that we're working with. Okay, so this is 1/2 integral. I'm going to distribute that u to the 3/2 minus 2 u to the 1/2 du. That and that cancel. What was u? U is x squared plus 2. So this is like that. Okay. Questions on that? I want you to do that one. Okay. So du, if I take the derivative of this, I get 1 over the square root of x minus 8, because this is really x minus 8 to the 1/2, so 1/2 that. Okay. Dx. And then the chain rule says I would multiply by the derivative of x minus 8, which is just 1, so that's all of it. Okay. So now I've got the square root of x hanging around, which is a little weird, but we'll deal with that in a second. So I've got u to the 6th. Got 2x, and then I've got a dx, which I can sort of rewrite all of this. 2 square root of x minus 8 du equals dx, right? And that's a u. So 2u du equals dx. So those 2's cancel. Really, the only thing I'm worried about is this x down here. And so we can get x by itself by taking u squared plus 8 equals x. Oh, this one, it shouldn't have. So there we go. So I'll take the square root of u squared plus 8 down here. Which is weird. Was the square root over all of the x minus 8 or just the x? Just the x. Okay, that makes it easier. Okay. Because that changes this then too. Okay. So let me do that in like orange or something so that it's just the square root of x. Okay. That makes it easier because now what we can do, I want to show you another little trick that I just noticed and remembered. So if I've got the square root and I'm taking derivatives of square roots, that's fine. But I would get u minus 8 squared equals x. And if you get rid of the square root by squaring both sides somehow or something like that, this is still a valid substitution, and it still gives me a valid relationship between du and dx. So I could take the derivative of this and get 2u minus 8 du equals dx. And sometimes that might be an easier way to get dx by itself in terms of u. Okay. So there's a relationship between du and dx that I can fit in right here. Okay, and I've already got that there. And so I've got u minus 8 is equal to the square root of x. That also comes from this, right? So I've got a bunch of stuff up here. Let's get rid of this one and redo the substitution. So this is equal to the integral of u to the 6th. I've got the square root of x is u over 8, u minus 8. And I've got this 2 here. And then we said dx is 2u minus 8 du. That's really nice because those cancel and those cancel. I get u to the 6th du, which is u to the 7th over 7, and a constant, which is the square root of x minus 8 to the 7th over 7. So, okay. You might recognize right away if you leave it as the square root that du equals 1/2 square root of x dx. And we have that right there. So maybe that would be the easier way in this case, just to recognize that those two circles contain the same thing. So you can take this as equal to du. And this was u to the 6th. It could be faster, but I kind of wanted to show you this trick with the solve for x and get dx by itself real fast. Other substitutions you want to talk about or other things you want to talk about? Okay, let's move on to 5.6 really quick because it's not really that much different. We just have to do evaluations now. So let's say I want to evaluate from x equals 3 to 7 of x minus 3 to the 5th dx. And this is a nice substitution problem where I'm going to take u equals x minus 3. So du equals dx. And then this whole thing turns into x equals 3 to 7, u to the 5th du. Okay. But at this point, and I explicitly wrote in the x variable equals 3 and the x variable equals 7 because those are the variables that I'm calling 3 and 7 when I'm evaluating stuff, right? When I'm evaluating this integral, I plug in 3 for x, I plug in 7 for x, I take that difference, and that gives me the definite integral. Okay, I've already changed all this other stuff to u's. I need to change these variable values to u's as well. Okay. So if I put x equals 3 into my u substitution, I get 0. I put x equals 7 into the u substitution, I get u equals 4. So I need to change my bounds of integration as well when I do the substitution. Okay. And then I get u to the 6th over 6 evaluated at u equals 0 and u equals 4. So this is just u to the 4th over 6, or sorry, 4 to the 6th over 6, which be 2 to the 11th, which is 2048 over 3. So on these, they're not really that difficult, and I don't actually have to go back to my x values or the expression in terms of x if I substitute these guys as well. Okay. So that makes these a little bit faster. Let's maybe see another one. Let's say I'm going to do the integral from 0 to 1 of r square root 1 minus r squared dr. So I'm going to do g equals 1 minus r squared. So dg equals minus 2r dr. I've got an r dr here, right? There's r dr. So I'm going to do dg over minus 2 equals r dr. So this turns into r equals 0 to 1, because I want to make sure that I keep track of what these values are. Are they r values or are they g values? Right now they're r values. I've got the r dr, which becomes dg minus over minus 2. And then g is the thing that's under the square root, so this is the square root of g. Okay, so now I can turn these into g values. If I put 0 into here, I end up with 1. If I put 1 into there, I end up with 0. So this goes in the opposite direction now. And I have g to the 1/2 with a minus 1/2 on it. Okay, so this is minus 1/2 g to the 3/2 over 3/2 evaluated at 1 and 0. So when I put 0 in, I get 0. And then when I put minus 1 in, I have minus 1/2 times 2/3. Because the g is 1, that turns into 2/3. So this is positive 1/3. Yeah. Where the G equals 1. Here's my substitution, right? If I put these guys into here, you put R equals 0 in here, you get G equals 1. So when R equals 0, G equals 1. So that's where I start my integration. When R equals 1, put R equals 1 in there, you get 1 minus 1, you get G equals 0. That's where you end your integration. I mean, sort of the idea is, if I wanted to carry around R values, they'd be R values equals 0 to 1 and so on. And then at this point, I would have changed things back from minus 1/2. I would have had this 1 minus R squared instead of the G. And then I'd have that over 3/2. Okay, but this is sort of like an inside function still. And I'm going to evaluate this both at 0 and at 1. So instead of evaluating it at this point at 0 and 1 and plugging it in, I'm taking this blocky value here, evaluating it as 0 and saying, I already evaluated it at 0, I got 1. So when I get to this point, I can replace this square with just 1. And then when I get to this point, I can replace the square with 0 because I already evaluated the square bit at 1. So you just do it earlier rather than write down all the replacement algebra later and then do it. And since the replacement algebra might be replaced in 8 different spots, doing it in 8 different spots doesn't make as much sense as doing it once early. Sort of an efficiency thing there. Try maybe what looks like my substitution here. Yeah. So the minus sign has a positive slope. So the derivative of this is the positive cosine, or sorry, not the minus cosine has a positive slope. So the derivative of the minus cosine is the positive sign. Yes. And then the chain rule says I have to multiply by 3. And then I get a dt. So I have this bit of the dt and the sine of 3t right here. So that's going to be du over 3. So this is the integral t equals 0 to pi over 6 of u times du over 3. Okay. At t equals 0, the cosine of 0 is 1. So 1 minus 1 is 0. At t equals pi over 6, the cosine of pi over 2 is 0. So this goes to 1. Okay, so 1 minus cosine of 3 times 0 equals 0. 1 minus cosine of 3 times pi over 6 equals 1. And that's where I get those guys. And then I have u over 3 du. So this is the integral. Well, I can do the antiderivative first. So I get u squared over 6 evaluated at 0 and 1 is 1 over 6. Okay. The last part is finding areas between curves. but we'll just hold off on that instead of lecturing that this week too. So this is just more substitution stuff. The first part of 5.6 is more substitution stuff with definite integrals instead of indefinite integrals. And the main trick is, well, substitute for the values too, not just the expressions, also the values. Any last questions? Yeah. So it looks like this. Okay. We're supposed to integrate this. I think the first thing I'm going to do is I'm going to take u equals the whole square root. Reason I think that, when you take the derivative of a square root, you end up with the same square root, but it's in the denominator, right? So having that same square root in the denominator next to the dr makes me think that I'm taking the derivative of this entire thing and putting it down here next to it. Plus, I've got the chain rule bit here, because the chain rule bit, the inside thing is going to be 6 times 2r minus 1 just by itself is going to be the derivative there. So this part also belongs with this, this, and this being the derivative of that big square root. Okay, so let's actually do that the way that I was telling you before, because I don't want to actually do the derivative of the square root, because square root derivatives are tricky. They're weird. So I'm going to rewrite this as u squared equals 3 2r minus 1 squared plus 6. And then 2u du equals 6 2r minus 1 dr. Okay, there's that bit for the dr, right? Okay, so move this over here, over 6, canceled on that side. So I've got the dr times the 2r minus 1 here and here. And then I've got the integral of the cosine of u. I've got a u down here. And then I've got a square root of 2, sorry, not square root, the 2r minus 1. Here it goes 2u over 6 du. See where everything went? Okay. Those guys are nice and cancel. You get 1/3 cosine of u du. The integral of the cosine is the sine. So I get 1/3 the sine square root 3 2r minus 1 squared plus 6 and a constant. we're out of time. I'll see you guys Monday.